if you have not registered for Flying High or you don't know what it is, you definitely should go here and read more about it. Uh, Flying High is our annual aviation event. This is our fourth one. The first two we did in person. Last year was virtual and this year will be virtual, but we're shooting to do next year in person. Stellar lineup. Let me just show you some of the speakers that we have confirmed. It's 8 hours, so it's one day on Zoom, and so lots of great people. Hopefully, most of you have heard of these names. Some of you may even be in the audience. Very excited about Steve will not be presenting this year. Gad will not be presenting this year, but just about, and it won't be Martha, but it will be somebody from Gen H2. So, and Jared, we need to update your picture if you're here, but a great lineup. And so you will definitely, I lost my, oh, I'm still on. Okay, that's it. Sorry. So that's November 4th. $75 to attend all day. Right now is early bird special. So you can get your tickets for $56.25. Not bad for an all day event. And you can use early birds fly high as the discount code. Let me put this link in the chat also to this newsletter so you can get all of this info. Students and faculty attend free. You can email Bianca at hi-sky.net from your university email address or the exclusive academic code. And so make sure to do that. And then here's I believe the direct registration link. I'll give you that. And next, again, these are in no particular order. I'm excited about this. Christine, would you like to come on and talk a little bit about this workshop?
Sure. Can you hear me okay?
We can.
All right, great. So Danielle has the link to the event page right there in the newsletter. The event is going to be actually a day and a half of discussions. The first afternoon will be basically sort of setting the stage of the current state of play and identifying some challenges and opportunities from our panelists. So we're actually going to have an ecosystem panel, and then we'll have a compliance panel, and then we will hear from National Resources Canada to talk about the Canadian Hydrogen Codes and Standards Roadmap. And then on day 2, we're going to get into
Sorry to interrupt, but how do I? Oh, sorry, so sorry to interrupt. How do I get to the program or agenda?
No worries. So
You can share if you want. Do you want to share it? If you
Okay,
have it
that's
handy,
fine.
or I can.
And I'll drop the link in chat for everybody.
Sure.
I'll go into share here. Make sure I get the right screen for you. Okay, so this is the event page, and then the agenda. You can click on the link there, but it's a hybrid event, so we will have in-person attendance in Washington D.C., and then we have online attendees able to join and fully participate. This is intended to be a discussion-based event, although on day 1 in the afternoon, as I mentioned, we're going to have 2 panels. One will be on the hydrogen ecosystem, just talking about kind of the state of play of where things are right now, and maybe some challenges and opportunities within standardization. And then our compliance panel will, dig into things like regulations, codes, other sort of third-party types of conformity assessment activities that are either in existence or would be beneficial to support the hydrogen ecosystem. And then we will have Natural Resources Canada talk about the Canadian Hydrogen Codes and Standards Roadmap. ANSI also held 2 webinars in March where SDOs came and spoke to their portfolios and how to get engaged. And then we also issued a draft standards landscape, which includes standards from various developers and allows you to sort by life cycle and various other technical metadata to kind of identify the standards that you need. And so this roadmap was actually done in Canada in 2023. And so between our our landscape and their roadmap, it provides us a pretty good snapshot of where things are and kind of where they need to go. But the Canadian roadmap obviously includes the perspectives of Canadian stakeholders, and we will be leveraging all of the landscaping and road mapping activities to date to dig into deeper technical dives on day 2. So we'll talk about 4 areas that we've divided it into is production, storage, and carbon capture, distribution and transport, infrastructure, and then end use applications or utilization. Uh, and these will be moderated discussions that will explore these 6 areas. So sort of what's the desired end state, talk about, when we think about the end state, some of that is going to involve some form of conformity assessment or may not include some form of conformity assessment, maybe some challenges in implementation of the existing standards, identification of gaps in standardization, where coordination is needed. Imagine this from, hydrogen itself to specific sector, specific applications. So where do we need to really increase the information awareness or do formal coordination between standards organizations to better provide the resources needed for industry, and then R&D needs. There's often missing data, so where can we help fill the gaps to help bring standardization to the marketplace, which will then also help with safety, cost, interoperability, etc. And then after all of the discussions, we're going to try to gauge industry's perspective on where they want to go next. Do we need to continue to dig deeper into the topics? Do we need to do a roadmap? Or do we need to kind of roll up our sleeves and just start working on the recommendations? So after we, finish the discussions, we really want to get an idea of what the needs are from the stakeholders. All of these recommendations will be published in a publicly available report sometime in probably the late July, early August timeframe. Registration is still open for this. If you're in DC, obviously, it's about a week away. It is exactly a week away. So if you're in DC, feel free and try and register to come in person. We still have space. And if you are not DC based and you'd still want to join us virtually. It's really the best way to highlight your needs, and we will publish that and incorporate those comments into the final report. So yes, that's basically what we're doing next week, and we welcome your engagement. Hopefully this will be helpful to you all too. For one, to understand standards, and 2, to influence, what happens next.
Thank you so much, Christine. Please give Christine a virtual applause because I just want to say, for those of you who aren't familiar with Christine, she came out of Gamma, which is an aviation nonprofit, or I guess it's sort of more of a lobbying. I think Gamma and 501(c)(6).
I mean, we're a trade association,
Okay.
so nonprofit member-based trade association. So yes, and I worked with the Electric Propulsion and Innovation Committee, and hydrogen was on the areas that we were discussing at least before my departure.
Yeah, awesome. And then, most of us are probably familiar with ANSI. It's not just aerospace or aviation. So from my point of view, this is a massive opportunity for aviation to have some representation in a published work. I've been complaining for years, nearly a decade, that every time we hear about hydrogen aviation, it's in the margins of a hydrogen, roadmap, or it's in the margins of like an AAM roadmap. But we've never had an opportunity to be a voice for aviation at such an early stage. So I highly recommend, and I really, really, really think you should go. If I was there, I would definitely go. I wish I could. It's just not feasible right now. But maybe we can talk to Todd about that as well. I kind of thought it might be good to talk about sort of like what message we want to deliver. So we can talk more about that offline, Mike. But attend virtually. It's free. If you're in the area or if it's feasible for you to drive, I've never seen an opportunity like this for aviation to be directly involved so early. So we need to participate.
I
Go ahead.
certainly think it would be helpful. listen in on the afternoon of day 1, but during day 2, these discussions are gonna run concurrently. So, for example, we might end up having infrastructure before lunch. We're not gonna force people to talk for an hour and 15 minutes. If we conclude our achieve our mission, we'll move on, but the, infrastructure and the utilization and use applications discussion, I think, will be particularly of interest. I mean, obviously, the storage will too, but I really think a lot of the storage things when at least my time at Gamma, we talked a lot about airports and codes and things like that. So if you have limited time, I would say these sessions are going to be really important. We're very fortunate to have Earl Lawrence from Joby Aviation joining our panel. So obviously some of the feedback that we get there will be incorporated into the report. But at the end of the day, when we're talking about the gaps and the needs from a regulatory and a standards and code standpoint, that's really day 2. And so you'll have the ability to chime in live or even just answer these questions live on the Slido and make sure that they get incorporated. One of the things that we talked about in our panel prep this morning was, even just standardizing too early and some of the nuances that come with that as well. So don't think it's like, what do we need to do now? But it's also thinking strategically about what we should wait on and what information we need first before we can get to standardization. So
Thank you so much. And by the way, I've been only including the registration link simply because for me it was kind of hard to find it from the original page, and so I thought, well, let's just get them registered and they can find the program later. But I would like to include that link because we can send out on Thursday. I can say like program as well. So if you want to send me that direct link, that would be helpful.
And I'd just like to say,
Mhm.
Christine, thanks for your leadership here, bringing all these different standards organizations together. I'm a member of SAE,
the new fellow.
yeah, AE5H, right? And so there's a lot of work being done. I know about SAE, but the other standards organizations, I really appreciate your leadership, and we really missed your leadership and Gamma and everything else. So nothing happened in the U.S. as far as Gamma for H2. So it's been tough to endure.
Well, I certainly miss my Gamma family. It's good to see your face, Mike.
Likewise.
Awesome. And then, so to that point, so I forgot I wasn't screen sharing. Christine, I was saying I'll include like a V program section
Mhm.
here in our next letter. Okay, so to that point, may seem unrelated, but definitely not. Last week, I had the pleasure of interviewing Val Mitikoff, former CEO of ZeroAvia. And in that interview, well, we talk about a lot of wild things, but we also talk about if you need to watch the whole thing because in the beginning we talk about why he left ZeroAvia, but in the end we talk about like what would be different, and he gives specific things that Christine, I even think that there's a part of the interview that we could even use in one of the presentations. It's towards the end, but he talks about what they're moving. The company's basically moved all their operations to the UK, and he talks about why, and it gives the United States a very good sort of roadmap on what we can do here. I mean, it's short. We only talk about that for like maybe 5 minutes towards the end, but I think it would be extremely valuable to, hear where they've not really had success and where they have had success and why. That is something to consider. We also talk about some funny stuff in here. So it's one of my favorite interviews that I've done. And let me just get you, well, you have this link, but I'll just give you that link.
And I can
Okay,
share
cool.
this with Christian Thiele of SAE International, who'll be moderating the end use applications discussion. And I see David
Mhm.
Frank is on as well. So, but yeah, so I can make sure maybe Christian will have some ideas on how he wants to kind of carve that in.
Cool, cool. And it could even be like in just like a discussion part. Maybe it doesn't have to be part of the official agenda, but I wanted you guys to see it prior to the event. So you would just kind of, and you could even maybe just touch on a couple points. Cool. Okay. So make sure to subscribe. High Sky Pod is now on Apple Podcast, Spotify. It's been on YouTube, but we're very excited to now officially be on Apple and Spotify. So we also have a joint course with AIAA on the first ever sustainable aviation fuel technical course. And that is in starts September 22nd. Here's our instructors. I think some of you are here today, so welcome. It's 5 weeks, 11 classes, 22 total hours every Tuesday and Thursday, and then there's the last lecture is on a Friday. And let me just give you the link to enroll. You do get a discount if you're an AIAA member, as many of us are. So I'll give you that link. That's going to be a very good course. And you might be thinking, why staff, Danielle? I thought you guys are hydrogen aviation. Well, staff provides a road, sort of an intermediary link to hydrogen being more, bringing down the cost of hydrogen and increasing the offtake, because it can be used to produce SAF. It's a feedstock. So that's my take on it, is that it's not SAF or hydrogen, it's both. And SAF is an easier to implement fuel because it's so similar to jet fuel. You don't need a new infrastructure to use it, and it can lower the cost of hydrogen. So it actually helps the hydrogen case for hydrogen aviation. Okay, next up, I told you these are in no particular chronological order. I'm jumping all over the place. But there's a group called the Southeast Hydrogen Energy Alliance, and they're not just aviation, they're everything. This Thursday, my 50th birthday, I said last night, oh, I'm going to be a half a century. Oh my gosh, that feels weird to say. But on my 50th birthday, I'll be giving a talk with John Piasecki and Ken Swartz, who also, I believe, is here. And that's going to be a really exciting conversation. Ken's going to talk about what he experienced with United Therapeutics, who's done some really cool stuff. First piloted hydrogen helicopter flight, and all sorts of things that he learned there. So it will be like kind of the exclusive on that. And that is on June 18th, a week from, or this Thursday, not a week from anything, it's Thursday. And so let me give you the link to that. And also, Christine, I mentioned this to you, that this is a great time to also promote your workshop. So make sure to attend. It's a non-aviation group, and they have great attendance. They're very similar to the HYSKY Monthly webinars. So it's free to attend. I recommend all of you, if you have something to say or you want to tap into a new audience that's not really part of aviation, but very much part of hydrogen, then this is a good one to go to. And then last, for me, our 2025 impact report is finally available. We had in 2025, we had 4,500 webinar viewers. We helped facilitate 75 job connections. We certified 126 professionals in this should say zero carbon aviation. I'm not a fan of zero emission because technically it has steam, water, vapor, still an emission, right? And we launched HYSKY Connect, which has over 500 members and generated an estimated 300,000 in volunteer hours, volunteer-driven impact. That's a huge accomplishment. So you can see how our community is advancing. I will stick that link in. And because of this, we very much depend on donations. So consider making a donation. And I'll give you that link. I know I'm overloading you with links. This is my last one, I promise. But consider even if it's $25 one time or monthly, it all helps. It helps a lot. So, and then I'm not going to provide a link, but those of you that are part of HYSKY Connect, you know that we are in the process of migrating. We were hosting on one platform, and we decided we didn't want to pay them $3,000 a year anymore. And thanks to Claude Code and other AI, we basically built our own membership platform, customizable. So comparable to like Member Suite and others, we're pretty proud of it. If any of you are spending a fortune on membership sites and you're interested in having a customized one that is essentially free and you want help to build it, reach out. We'd be happy to assist in that for a small fee or donation. And if you want to be part of the WhatsApp group that is in the beta, like if you want more features, you can text 214-444-9138 to join the beta WhatsApp group, which means you access the member community and you say, hey, I wish I could do this. I can't. And we'll build that in. Okay, so now I'm going to scroll back up to the top, and that is the end of my spiel. And I will pass it over to Mike. Mike, I'll continue to share. Well, and so you can start with EAS and then our speakers for today.
Yeah, so as Danielle showed before, we're doing the 20th Electric Aircraft Symposium. It's really Ken Swartz is really the brains behind it. But Ken and I are both on the board for HYSKY, and so we've got some hydrogen content in here. The early bird deadline is Saturday the 20th. Danielle sent out a special code where you can take off even more off the early bird registration rate of $200, and you can take off $50 off of if you want the PDFs and the PDFs and the video recordings of the event.
I'm so sorry to interrupt, Mike, but I just wanted to quickly say, put a 1 in the chat if you're going to Oshkosh. Put 2 1s if you're going to Oshkosh and EAS. Keep going, but I'm just curious who all.
Yeah.
I'll be.
And you can see we've got lots of sponsors already, and we can't even we keep updating the graphic, but we've got a couple more already to add. And I just want to highlight the program here. This is the online program. We've got this session on Sunday morning on hydrogen that our fearless leader Danielle will be chairing. Nick and Gara. We got 3 PhDs on this session, so it'll be really great. Anita Sengupta, the CEO of Hydroplane, and Josef Kahlo is coming over from Germany to talk about H2Fly. And we've also got some other great stuff. We've got David Smith, so he'll be talking about the Unither bioelectronics, hydrogen helicopter, and also other work that they're doing. You'll see here that Ben Chiswick from FEV Aerospace is chairing that session. And should I go ahead and transition into my intro of our featured speakers, Danielle?
Yep.
Okay, great. I didn't intend for that, but it just worked out really well. So yeah, so truth in advertising, or the state, state this relationship. So I met Ben a couple years ago, and was really impressed with the work that FEV does. So I'm an aerospace engineer, got a mechanical engineering degree, but I've always really been interested in propulsion, combustion, heat and mass transfer. And so this was like really a match made in heaven for me to be consulting with FEV. So Ben and Satyam will be talking about the history and past, present, and future of FEV. But I'll give you a little bit here because I'm a nerd, so I like the story behind the story. So they're based in Aachen, Germany, and I know everybody knows Aachen as the seat of the Holy Roman Empire. That's where Charlemagne or Karl the Great had the seat. And there's the university there. In English, it's called Aachen University. So they developed this combustion research center. They spun it out into FEV. Originally, okay, here comes nerd alert. Originally, it doesn't stand for this anymore, but originally it stood for the Forschungsgesellschaft für Energietechnik und Verbrennungsmotoren, which is a research association for energy technology and combustion engines, which really kind of sums up the basic work they did. So they started out consulting for, they started out working in the automotive industry, things like, piston engines, diesel, hybrid electric, hydrogen electric, battery electric. And so they now have FEV Aerospace, and I've been really pleased to help to work with Ben and the team. And I'm always just really blown away by the technical depth and breadth of the company in these types of technologies, not just propulsion technologies, but and the applicability to aerospace. So the 2 speakers, so Satyam, I guess I think we met before. Satyam Joshi, He's a PhD technical leader at FEV North America, 13 years of experience in simulations, controls, calibration, and testing of propulsion systems. He got his doctorate degree in mechanical engineering from Michigan Technological University, specializing in advanced propulsion systems. And he works across FEV and multidisciplinary teams for integrated solutions, spanning controls development, hardware integration, validation, functional system performance, and supporting customers from early concept definition through testing and deployment readiness. Ben Chiswick is a business development director at FEV North America, where he partners with OEMs, government organizations, technology leaders across aerospace and defense to define and deliver advanced propulsion, power systems, hydrogen, and electrification solutions. And there's kind of a typo in the title. It said for vertical flight, and it's really, that's one facet, but they obviously do everything related to flight. And fun fact: so Ben got married like 3 weeks ago now. So he was out for 2 weeks on his honeymoon. So and then he got sick last week. So here he is, hopefully back at full strength. His background actually came from motorsports, and he's also an avid golfer. So Ben, I hope I embarrassed you enough that you can take it from there.
Everybody
very much so.
give a warm welcome, a virtual hand clap, all that good stuff to FE.
All right. Thank you very much, everyone. Hopefully you're seeing my screen come through okay now.
Yep, looks good.
Perfect. Yeah, Mike, thank you very much for the intro, especially your explanation of what FEV used to stand for. I was waiting for that to come up as a question and dreading having to answer it. You always do the best job of answering it, so thank you. What we're going to cover today is very much as Mike suggested or described rather. So I'm going to start off and kind of give a little bit of a level set on FEV, who we are, what we do, and kind of how we work. And then I'll hand it over to Satyam, who will dive much deeper into some of the more technical work that we've done of late with respect to hydrogen fuel cells. So with that being said, we'll get into it. So Mike gave a very apt bit of background there, but overall, we've been around for nearly 50 years, and we've got over 45 subsidiaries spread right around the globe, 5,500 roughly employees globally. So that allows us to deliver a huge amount of different capabilities right around the globe, irrespective of where our customers might be, where they might be operating, or the kind of work they do. Spread around the globe as well, we've got a huge number of test cells, and we'll kind of come on to a little bit of that. And we're very proud of the fact that we have around 200 patent applications per year. So we very much carry kind of a good academic backbone right through the company that really keeps us kind of at the forefront of innovation and pushing things forward. So we're always ultimately an attractive proposition to partner with industry and to work. Okay, so we're an engineering service provider, but that can mean many things, and there are many service providers out there. So what is a little bit different about us, or that kind of marks us out? Well, number one, we have rapid development capability. So we pride ourselves on being agile. That goes hand in hand with being a turnkey partner. And what we mean by that is being able to go from a completely clean sheet right through to a validated prototype system with the ability to do all of the virtual verification and validation as well as the physical. So we can really close the loop on all of the simulation and all the analytical work that we're doing, and then hand that off to our client. And again, we'll come on and elaborate on that a little bit more. Knowledge transfer is a big deal for us. So it's one thing to go and deliver a design or a specific service for someone, but all of the underlying processes, methodologies, how we've used the tools to get to where we've got to is, of course, really important knowledge. So people come to us for that knowledge transfer very often, and very frequently we have our engineers co-located with our clients, whether that's at their facility, sometimes it's at ours, sometimes it's even both. Flexibility is kind of our byword to help people push forward. Global reach, I've kind of already touched on, and technology agnostic. Mike had mentioned kind of our very first beginnings, really, all in fired engine combustion. That's something we still very much carry through now, but over the years, we've broadened our portfolio in terms of capabilities, in terms of technologies. So when we think about propulsion particularly, it's piston engines, rotary engines, with whatever kind of fuel you might want to imagine. It's hydrogen fuel cells, hydrogen ice, and then of course as well, electric motor, power electronics, battery technology. So really anything from energy storage right through to wheel, propeller, turbine, track, whatever it might be, is something that we can touch and that we can engineer together for people. And then lastly, completing this wheel is IP ownership. Again, that keeps us quite, I say, easy and accessible to work with, whether that is for a new engineering startup who are obviously trying to get started up, develop IP and kind of get to market, or very often on the government side as well, which is a huge part of what we do. The government want that IP ownership. So again, we don't do any kind of licensing or holding on to IP. It keeps us very easy to kind of turn the faucet on and off. That keeps us easy and accessible for people. All right, this gives a little bit more detail of where we're specifically at in FEV North America, where Satyam and I sit up just north of Detroit in Auburn Hills. Lots of golf courses around here, as Mike has sort of alluded to there. And here we've got around about 400 employees. So we're the biggest campus outside of Aachen, Germany, meaning that we can really deliver across our full range of capabilities of the group, but locally. Very importantly, we've got about 100,000 square feet of development, test, and prototyping space. That's split across 4 different buildings locally here. And again, flexibility is really the byword there. So we're not a traditional, let's say, test house where you will issue us a test procedure and say, here's my transmission, motor, engine, whatever it might be, go test. We very much exist in that space where it's the first time that a system is coming to life or the first time it's being integrated into a broader system or with its partner subsystems. And excuse me, inevitably something's going to go wrong, something might fail, integration issues. So we carry the engineering expertise around us to be able to problem solve those, root cause those things, again, to be that development partner. This gives just a little bit of a sense of the very recent past. As Micah kind of suggested, we've been around for nearly 50 years now, but FEV Aerospace as a brand is quite new. We've done aerospace work for quite a number of years, but recognizing that we wanted to grow and make aerospace a really strategic focus for the company, we decided to start our own brand and give it that focus both internally and externally as well. Excuse me. So here you'll see just a little smattering of programs that we've delivered, we're able to talk about. 99% of everything we do is unfortunately under NDA, so we can only ever share so much of it. But this gives you just a little bit of a flavour. I mean, coming right up to date, 2026, you see some of the bits of thought leadership that we've presented that we will be pulling, excuse me, sorry, we'll be pulling from today, particularly in Satyam's section of the presentation. So little bit of an eye chart here, but this kind of lays out in more visual terms where we work in the project life cycle. So it's the full V cycle. What's quite interesting is you'll see sort of the top left and the top right preceding what is usually on the V cycle, product strategy, and then over on the right, industrialization. So that's sort of the on and off ramp to FEV. So we have a consulting team within the FEV group. Actually, just this year were nominated by Forbes as one of America's best management consulting firms individually, that we're quite proud of. But they really help customers with their product strategy initially. So I say we can do a clean sheet, but it's a case of how big is that sheet of paper? What shape should it be? How should people position themselves in the market before we then go and obviously engineer those systems through the normal V cycle? I mean, out on the back end, they're doing a lot of operational consulting, helping people with supply chain, helping people set up their sourcing as well. Excuse me. So overall, that kind of gives you a bit of a better sense for how we lay out across the V cycle. Okay.
Feel free to get some water if you
Mm.
need to. Many of us are recovering from illnesses, so it happens.
It's all right. I'm on the upswing. So before I dive into just a little bit more detail of some of the capabilities and some of what we actually do, here you can see a little bit of again of a sprinkling of some programs that we're able to share across these different sort of sub verticals. And I think one thing which is quite clear that always comes through with this is there's a little bit more of a European flavour to this. And that's because we started our aerospace focus in Europe a little bit earlier than we did here in the US. So over time, kind of part of my mission is to very much balance that up globally. But again, you can still see nonetheless a good sort of balance of different types of companies, sizes, and just gives you a sense of the multiple different types of company we work with and areas that we can plug into. Okay, coming on to what do we actually do within that services world. So it's really divided into 6 pieces. Number 1, electro-hybrid propulsion engineering. So that's really anything and everything motor, power electronics, battery, or integration thereof. Then next, strategic and technical consulting. That's delivered by the FEV consulting arm that I was kind of just speaking to a little bit. Systems engineering is a huge part of what we do, and I'd already described a lot of the different disciplines that we operate across. So naturally, when we bring multiple of those to a larger program, we have to bring systems engineering to the party as well and really be expert in doing that so that we can integrate across all of those things. And in some cases, we're brought in to be systems engineers for our clients to help them weave their products, programs together, or maybe to, in some cases, put in systems engineering processes and tools. Also, under that heading, we cover cybersecurity analysis as well, and some functional safety work and support as well. Software engineering and data science is an increasingly big part of what we do. So whether that's control software and algorithms for motor, for engine, for fuel cell, for battery management systems, or then the prognostics and hum systems that support those, that really comes under that team. And as you might imagine, is a growing part of what we do, especially as we weave in more and more AI and into our tool sets and how we work. Aeromechanical systems. So, I'm a transmission engineer by background, so I identify with this very readily. But the mechanical elements of bringing all the different things together that I kind of already referenced, but particularly gearbox work and aeroacoustics a little bit as well. And of course, last but absolutely not least, hydrogen propulsion and also infrastructure as well. So obviously we'll come back onto that in a bit more detail. I did want to touch on the hybrid propulsion engineering and give everyone a bit of a flavour of that as it's kind of sitting downstream of the fuel cell. We'll speak to number 1, battery engineering is a huge focus point for us. So FEV Group actually design, built, owns and operates the world's largest independent battery test facility, which is located in Germany. So again, that's something we're quite proud of, and it gives us a really powerful, not only validation capability, but prototyping capability as well. So we can do all of the destructive testing that we need to, all of the really difficult kind of niche tests. And that facility also allows us to do very low rate production to kind of bridge between the 3, 4, 5 quantity prototyping and the more hundreds that really the battery pack suppliers or battery cell suppliers want to support. There's a little bit of a gap in the middle there, and we often find ourselves positioned in that. Next, copper bird testing. So, really all of the description of systems that I'd already covered. So whether it's battery, whether it's motor controller, inverter, DC-DC converter, motors is, we have to do copper bird testing. So being really the glue that fills different gaps that people might have, whether that's in plant modeling, whether that's physically setting up multiple motors under test or motor durability testing, something we're really well positioned for. I see the integration of all of these things together is something that we have to do an increasing amount of. Certainly when we think about hybrids and we think about small piston engines together with electrified systems that obviously we're seeing more and more, we have a foot in both camps. So that really means that it gives us an ability to not only understand all of those subsystems at a very deep level and plug gaps that people might have in their expertise, but how we integrate those together. And it's not fair necessarily to consider the system integration as its own discipline because it's interwoven into everything, but equally it deserves its own call out. So we see a lot of people have issues there, so we find ourselves called upon very frequently for that. Sustainable fuel development is something we do a small but growing amount of, particularly in our European base. So we're really well plugged into the Oil and Gas Climate Initiative. So we work with really all of the usual major oil and gas suppliers that you might imagine. And really a lot of that comes from our strong lineage in combustion engineering. But of course, as those stakeholders are looking at developing sustainable aviation fuels, gives us a natural position to be able to help them, whether that's on the consultation side, looking at market analysis, or indeed on the actual fuel development and implementation side too. So it's a very small piece, but I'm quite excited about that. Motor development, of course, makes sense. Then finally, power electronics. Again, really almost an integration piece where You find a lot of people are trying to find COTS systems that either won't integrate very well or they won't get the optimal performance. So again, we're called on for the power electronics quite frequently too. All right, getting on to more the main event. So hydrogen propulsion and infrastructure. What do we deliver here? I know this is a format that everyone here will recognize very well, but this is really to just underpin how committed to hydrogen FEV is. And the reality is we've been operating in the fuel cell space for probably 20 plus years. Of course, automotive to begin with. And whilst all of the different application parameters, nuances are different, Satyam will be covering that. We understand those very well. This gives you a little bit of a sense of that timeline. And of course, there's many road-going vehicles on there, but you've also got things like commercial applications. You've got trains as well. So again, very broad set of expertise across different sectors as well. And we like to think that working across all those sectors, exposing us to different tool sets, exposing us to different constraints, ways of working, it means that we can carry learnings from one sector into another and gives us really much more of a improved, rounded offering. Okay, so fuel cell design analysis, of course, big part of what we do and what we have to be able to deliver. But rounding out our hydrogen offering, fuel cell controls and safety analysis as well. Of course, the software piece has to go hand in hand, and we carry a model-based controlled software library, and that's across much of what we do. But we can leverage that, and it means that we can get people to a first operational prototype much more quickly with lower risk and in many cases lower cost as well. It just helps us deliver more effectively. Of course, fuel cell development testing with our global network of development facilities amongst all of our subsidiaries. We have a global network of hydrogen capable test facilities as well that underpins really all of what we do. Fuel cell integration, of course, you're thinking about storage, plumbing, packaging, supervisory controls of the storage as well. Some of those things which often get treated as secondary issues compared to the fuel cell itself. We're really well versed at engineering those and integrating into vehicles. So again, we're called on quite frequently for that. Something that people don't really know us for yet, but hydrogen electrolysis is also part of what we do. So we actually have an energy and resources team who I kind of characterize, they do the stationary versions of everything that everyone else in the company does. So stationary battery energy storage, electrolysis as well. And that really allows us to kind of round out our hydrogen offering. And last but not least, of course, looking at the ecosystem development and infrastructure. So that's really underpinned by our consulting colleagues. So looking much more at the business side of how does the hydrogen ecosystem need to work as we look forward? Where are the weak points? Ultimately, for us, helping our clients position themselves not just for today, but within that future ecosystem effective. Okay, so that being said, we'll nearly get to the interesting part with Satyam. But beaming this up as just a quick example of, again, some of where we have that hydrogen equipped test facilities really right around the globe. And we're only going to see this grow, obviously, as hydrogen grows and the call for that kind of work from within FEV also increases. Okay, so the last one from me is really to just collect together several pieces of what I'd already name checked. So we're really experienced across a whole number of different vehicle types, whether that's heavy duty, aerospace, non-road machinery, light duty, passenger car, of course, is really our lineage, but marine, rail, stationary, all sorts of different propulsion systems as well within that, a number of different fuel cell systems developed from scratch. And then also benchmarking and testing is a big part of what we do, whether that's cost benchmarking and teardowns, or of course performance benchmarking to go with that. So we deliver a very rounded service there. And again, that helps us allow our consulting team to help customers position where they want to be. So it's not just a case of here's what the technology roadmap looks like, but here's the roadmap supported by the technology that's incumbent today and how that's all operating, what the cost points are, what its availability is, and what its performance is. And of course, validation programs as well. So with all of that being said, I'll go round off now with a couple of examples. I'll flick through these quite quickly. We will just see a few different case studies of things that we do or are currently involved in. We've done a fuel cell, excuse me, feasibility work with Safran that we're quite proud of. Different fuel stacks. This, of course, one that I can't name, unfortunately. Love to. But then also round it out. I've actually done a fuel cell for the Paris-Dakar Rally. So, of course, this is quite close to my heart, being from motorsport. But again, it just shows you the breadth of what we do. And then equally here, an exclusive sports car application, but for very, very high-end OEM that's in Europe. So again, it just shows you the full breadth of kind of what we do. And again, not a huge lineage necessarily in aviation hydrogen, but it just shows you the range of different problems that we've tackled and ultimately the tool set and experience that we've got to bring to bear to tackle those. Last but not least, and this is just an example of an integration program that we can share with a company called Hyliion that we did a lot of work with here in the US, where we converted a fleet of their trucks to hydrogen fuel cell and did all of the surrounding subsystems for them, all of the vehicle level validation, and again, kind of shows you around the hydrogen storage system and controls and how we operated and worked. So with that being said, I'm going to hand off to Satyam, who's going to take the reins on the screen as well.
Yeah, thanks, Ben. We are able to see my screen.
We do. You'll just want to go to, there you go.
Okay. All right. Yeah. First of all, thanks, Mike, for the kind introduction. I do want to recognize my colleagues who actually were the lead authors for some of the content that I will be showing today. Max and Joel, they worked hard on some of the work that we did with regards to the specific adaptation of automotive fuel cells into propulsion systems for aviation applications. And we also are highlighting that it's not just adapting, but how do we optimize? So there's content that I will be showing on not just adaptations, but then how do you optimize the system for aerospace applications? So let's start here with what are we competing against? So we've got turboshaft engines, really high in power density, acceptable level of efficiency. And then you have internal combustion engines or piston engines, as we call them, more, let's say, slightly more efficient, but not as power dense, work really well in that 200, 300 kilowatt power range. And at a specific power level, they tend to be a little bit more efficient. So if you compare those two against what automotive fuel cell systems are, the automotive fuel cell systems are very low in power density compared to these two propulsion system options, but obviously quite a bit higher in efficiency, not really suitable for aircraft application. And what we're trying to get to is a target of at least a similar power density as the piston engines with better efficiency. So that's kind of the goal of some of the work that we've been doing, and how do we make these more suitable for aircraft applications. Some more, let's dive into some numbers here because we love to look at some numbers. So if we just look at this plot here on the left side, I have max system net power of the fuel cells and some startup production dates in the automotive and heavy duty trucking space as well. And this data is all about single stack systems. You know, most of the systems today are to a level of 200 kilowatt net system power. Again, focusing on single system, because you can, of course, stack multiple of them and create larger total fuel cell system power output. But for single stacks, this would be kind of the limit. What we are looking at startup production today. There are roadmaps in the trucking space to push to 350 kilowatt single stack systems, more in the 2030 timeframe. And then what we've been doing some R analysis as well as a lot of, let's say, announcements from startups to target about a 400 kilowatt fuel cell system for aircraft applications. If you put those numbers on a chart of gravimetric system power density versus maximum system net power, and this is in a log scale, the fuel cell systems are in a pretty low power density space here. I would say a medium around 0.4 to 0.5. The piston engines in the range of 0.8 to 1 kilowatt per kilogram. And then, of course, the turboshaft engines are quite more power dense on a system level. The trucking space is, if you were to expand that, do all the technologies that we can do there, they would be targeting somewhere in the 0.8 kilowatt per kilogram power density. And then for the aircraft application, the goal would be to target about the same level of power density as the aviation piston engine. So that would be the goal, target 1 kilowatt per kilogram on a system level power. Okay, so we want to get more power density. Let's start with where's the weight coming from for a fuel cell system. So we did a teardown of, we've done teardowns of multiple fuel cell systems in the automotive space, and we picked the one that was kind of the latest technology. And so it was about a 100 kilowatt fuel cell system, 125 kilowatts stack, and that weighs about 357 kilogram, along with its hydrogen storage system. And if we look at, of course, the fuel cell, 60%, the storage system, about 40% of the total weight. If we break down the fuel cell system into its different components, the stack assembly is the biggest contributor, followed by the cooling circuit and the cathode system, which is the air side, as the top contributors to the weight. If we further break it down and look at the details within the stack assembly, you have bipolar plates contributing 46%. Another big hitter is the housing itself, and then the end plates and frame. So we looked at this and tried to understand, what are the low-hanging fruits? Where can we optimize the most? And we identified, let's look at the hydrogen storage system, and I'll talk about how we address that for each of them. But look at the hydrogen system, look at the thermal system, the cooling system, then bipolar plates, of course, and the housing design. So these are kind of the key focus areas in all the projects that we've been working on to address how we can get more power density by focusing on these subsystems. So starting with the storage system, it is relatively, let's say, straightforward there. I mean, most of the automotive and heavy duty trucking, or even some of the locomotive applications, were using compressed hydrogen. Some of those applications also have transitioned to liquid hydrogen storage. So that would be kind of a rather easy step to do, is to move to a liquid hydrogen storage system, still operating in that 1 to 10 bar range. One challenge, of course, is the boil off and some losses due to that, but still manageable. And obviously, the huge power density increase or energy density increase you get from just switching to liquid hydrogen storage outweighs that hydrogen boil off loss. The other one that I mentioned was on the bipolar plates, and what is the new technology there, and how can we get to more lightweight stacks. So most of the ground systems, they are using stainless steel or some kind of graphite compound if you're looking for more durable stacks. Bifoils is kind of a hybrid between stainless steel and graphite compounds. And then titanium really pushes some of these systems, improves the power density as well as the durability. The next step there is to then, of course, look at some ultra thin and thin titanium. So these do involve some more advanced manufacturing methods like hydroforming. And so that is how you are able to push these to 7 kilowatts per kilogram power density. And then really thin metals with minimizing the non-active area. So that is design optimization combined with thin sheet metal combined with advanced manufacturing are some of the ways that we believe that we can achieve. So the green diamond here is where we have seen some work already, but really the goal is to achieve the target here of 9 kilowatt per kilogram. Then switching then to the housing side. So here's a couple of pictures on the housing in the automotive space. The Mirai housing design, the design from Refire Prisma, fuel cell as well. There's already, as you can see in that design itself, opportunities for lightweighting and some step measures that the OEM already did take. But in general, there's always opportunity for improvement, and we found areas for lightweighting in the housing and clamping system, balance of plant components, and those are, again, some of the just doing more iterations with your design, CFD, CHT analysis, structure analysis to get to more lightweighting. The other one that's a big one is, of course, the thermal system. As many of you are already aware, fuel cells are unique in terms of how they reject the heat as compared to the piston engines and also the turboshaft engines, where a lot of the heat is carried in the exhaust. Fuel cells have very little heat that goes out through the exhaust, and most of it is rejected into the coolant. So far analysis has shown is that it may not be the best way to match the power demand, peak power demand, to the peak power output of the fuel cell. You want to oversize the system a little bit to get the best, let's say, trade-off between the fuel cell weight itself and the weight of the thermal system and the efficiency of the aircraft itself. So it's a system level problem and has to be looked at with some tools, which I will talk about in a bit. So here's two charts. One is showing, if you were to size your fuel cell in a way that you run it pretty much at 90% of the load, you end up with lower efficiency there, especially if you're doing cruising at that load. The other approach is here, if you were to size your fuel cell system larger, then it brings down your the load during cruise, which then allows you to operate in higher efficiency and reduce the amount of heat rejection into the coolant by doing that. So that's one of the methods. We have found that slightly oversizing the fuel cell does help, but it has to be analyzed for specific aircraft for a given duty cycle, and there's some tools to do that. There are, of course, technologies, hybrid cooling systems, whether you want to use part radiator, part like a vapor compression cycle with the condenser that's with another refrigerant loop. So those systems do allow for better system level optimization, reduce the radiator size, reduce the condenser size. There's direct air cooling systems. I think there's a very good example from Intelligent Energy, and their system is quite impressive in terms of direct water cooling the stacks. And then, of course, a high temperature PEM fuel cell. So that would be a fundamental, let's say, upgrade to the fuel cell itself, and it involves a lot. And it's a challenge because the idea here is how do we adapt some of the methods, some of the products that already exist in the automotive space for aerospace applications. And the high temp fuel cell, great technology because it allows you to reject the heat at a higher coolant temperature, which reduces thermal size. Still has its challenges of durability, and you do need to size your stack again a bit larger for good efficiency. But on a system level, it's a larger tier up. So the idea is here to how can we scale up the automotive fuel cell and allow some of these manufacturers who have been producing fuel cells in the automotive space for many years now, give them a path to provide their products for aerospace applications. Another critical area of adaptation is compressors. So most of the fuel cells in automotive trucking space, they are single stage, good for 10,000 feet or so. But as we start to look at some of the higher altitude products in aerospace, you do need multi-stage charging system, and so that is kind of a, let's say, major consideration that would be necessary. I have a plot here showing as you go up in altitude, what kind of pressure ratio is really needed, and how the air pressure is dropping. So right around 10,000 feet is what a single stage air compressor can handle. Maybe you can push it up to 4.5 or so. But typically for about 10,000 feet high tech, you'd be okay with a single stage, but then pushing beyond that, certainly will need 2-stage. And of course, if you wanted to get more efficiency, you could split up the 10,000 feet into 2-stage compression, get some slightly better efficiency by doing that. But that's one of the major considerations. We also have seen that in the automotive and trucking space, not everybody uses a turbine. But in the aerospace that is kind of a must to have to recover the exhaust energy and maximize system efficiency. Okay, so it's not new that all of the requirements for fuel cells and aircrafts would reduce power density. I mean, we're looking for lightest weight. We're looking for long range, low cooling losses, high durability, reliable system, and everything would be then trying to point us towards oversizing of the fuel cell system. But the question is, how do we gain this power density back? And one of the big things that I have kind of touched upon, but not clearly stated, is make sure that this is a extremely integrated system. So kind of splitting it into multiple stacks or having, let's say, finding synergies between different systems when designing it has been the key for us as we are looking at redesigning some of these systems for aerospace. Bipolar plate design material, I talked about that. Along with that, the housing design, clamping system, and end plate design. So these are just fundamental design optimizations, just need more loops in the new environment, along with analysis. Thermal system, I also touched upon that. A compressor unit, expander unit optimization. So these are all the measures that we identified and would be key to adapting the automotive fuel cell system to aerospace applications. Okay, so that was on the fuel cell level. If we look at propulsion system as a whole, it's got two other major components. That would be a battery pack to handle some of the transient loads, and of course the storage system. So when we generally look at these problems, coming from a lot of research oriented company, we like to have the right tool set to make sure that we capture all the physics that is happening within all these systems. Because like I mentioned before, you just focused on power density of the fuel cell system, you size it small, but if you look at the cooling system impact of that, that may not be the right decision. So, and then further, the cooling system impact on the aerodynamics of the aircraft, that's also another impact. So the problem has to be looked at in on a system level and making sure that you're able to model effectively each and every component of the propulsion system. So this was a case study that we presented at Forum 82, focusing on how can we set up a multi-physics model of the propulsion system and the aircraft and do an optimization study. And we just did phase one of this. It's got a couple more phases, but it's taking us in the direction of doing system level optimization using modeling. So some specs of this aircraft: it's got eight lift rotors, two cruise propellers. We were targeting 400 kilogram of payload and range of 200 nautical miles, and maximum tow weight of 3,000 kilograms. So about four-seater aircraft, more for intercity travel. The tool that we developed here was, let's say, leveraging a lot of our know-how in the other space and taking the tool that is so far the leading candidate, which is GT Suite, and all of the work that we've done with regards to fuel cell, any other propulsion system. On a system level, this is a great multi-physics modeling tool, and a lot of our models are validated against the benchmarking we have done for different fuel systems, e-motors, batteries, power electronics. We have performance models from a range of vehicles and aerospace application components that has fed into this database. So this on the right side here, I have the basically GT Suite, which does all the propulsion thermal system modeling. And then on the left side, what we leveraged was an open source aircraft dynamics model called SWAF. That's from Stanford University, and it's available open source. So we tried to link the two so that we get the most, let's say, realistic or high fidelity dynamics of the aircraft model. And from our side, we have all the details of the propulsion system and thermal system model. Right now, it's a one-way coupling, so you get inputs of flight data, geometry, mission definition, and that feeds a power demand into the propulsion model. And then also altitude and speed, which impacts thermal management, fuel cell system operation. But we are working on, at the moment, closing the loop here so that we can do feedback on actual power, weight, aerodynamic impact. That way, this whole tool chain can become our go-to tool chain for system level optimization. So the first step we did here was make sure that the aircraft dynamic model was validated. We had some test data available for about 100 nautical mile route. And here I'm showing power on a normalized scale, so you can see the takeoff portion going up to maximum power on the lift motors, and then slowly transition into cruise climb phase. And then you enter your cruise phase here with the cruise motors, then deceleration, or sorry, descent, and finally do a hover before you land. So those were the different flight phases. And for each of the flight phases, we calibrated the model so we can match the aircraft dynamics to our test data. And overall, this was very well correlated model. The specific flight was done at the max altitude of 6,000 feet, max cruise speed of 320 kilometers per hour, about 168 knots. So we're very happy with the aircraft dynamics calibration. We took that same the aircraft dynamics model and tried to project what would be a target mission profile for an intercity route between, let's say, Detroit and Chicago. Our goal was to target more than 200 nautical miles, and this was right around that. And using that, we created a new power target profile. So that's very key for doing any kind of optimization. You want to know what your mission profile is, and this is what we use then this tool to predict or calculate for us. Some more details of the propulsion system model. So it's got all the different elements in here. So fuel cell modeled as semi-predictive. These approaches have come from our years of experience of modeling these components. Instead of getting into the details of solving all the electrochemistry, there's easier ways that are more, let's say, robust and also more closer to reality. And that's why we use certain models. So fuel cell, semi-predictive, high voltage battery using two RC branch equivalent circuit model, motor inverter. Most of this data comes from our own teardown analysis and benchmarking for loss maps, for rotational dynamics, inertias, BMS, thermal model. So for the thermal model at the moment, we've been using what is called semi-predictive thermal model, where it looks at the heat rejection and calculates the pump and compressor power consumption. And later on, the plan is to make it more detailed. Energy management controls, so determine how best to utilize the battery pack, how to balance between battery and fuel power. So those split is defined by our intelligent controller, and then a pilot model to make sure that we can follow the power request profile. Before we got into, let's say, doing an optimization, we want to understand what's the best architecture or what's the leading architecture before we get into doing more focused DOE. And many of the systems, they use, let's say, an eVTOL platform and try to add certain range extender components. And that would be kind of a battery dominant architecture where you're using a high energy density battery and then adding on a fuel cell system to get more range. And the other one would be a fuel cell dominant, which would be keeping the fuel cell as the leading propulsion device and then just adding some battery capacity to handle the transients and then manage load transitions on the fuel cell. So that's the fuel cell dominant. And right off the bat, when we looked at the propulsion system mass calculation, there was a significant difference, about 350 kilograms between the two for a given range that we were targeting. And yeah, so very clearly when we ran the simulations, we saw the same thing. A fuel cell dominant variant, you're running the cruise pretty much all on fuel cell power. The battery is just there to support the takeoff portion and then hovering portion before landing. Whereas in battery dominant variant, you're consuming the battery, fuel cell is pretty much running its best power point the whole time. And this approach is not really favorable from a weight perspective, and that's why we decided to then move forward with the fuel cell dominant architecture. Did some screening assessment on the payload capacity, so set the fuel cell power, set battery capacity to figure out where do we have the minimum. Of course, it would want to go to as small as possible, but then you look at the power profile and make sure that it's following the profile. And below a certain, this Pareto front, is if you want to call it, below this Pareto, you wouldn't be able to follow the drive cycle, or in this case, the power profile. And that was the key outcome from here, that okay, our optimization region is somewhere in this 300 to 450 fuel cell power system power max, and then high voltage battery capacity is about 18 to 24. So once we figured that out, we ran what we call as a genetic algorithm optimization. Just on a high level, I'll explain that is just a way that our tool allows us to explore what's the right sizing and understanding the different trade-offs that we would see between as we're modeling the complex physics of the system. So very important to set the model correctly, and then you can, of course, do a lot of these optimization algorithms with it. And here it resulted in showing that, okay, from a fuel cell perspective, we wanted a stack voltage of 450, max power 366, battery capacity of 22.5, 31 kilograms of hydrogen, and that would give us a 410 kilogram max payload for this duty cycle. Okay, towards the end of my presentation, I do want to leave a few minutes for questions. Key takeaways: automotive fuel cells need significant adaptation for aerospace use, with key barriers of power density and low temperature heat rejection. The key areas we identified for power density increase are storage system, the bipolar plates, housing design, and thermal system. You do need to take a holistic approach as you're looking at design optimization. So, like I said before, sometimes oversizing in a pack will lead to better efficiency, can lead to smaller thermal system, lower aero drag. And for the system level design optimization, try to have the modeling framework that captures the details of all of that is happening, the aircraft dynamics, thermal system, propulsion system as necessary, and make sure these component models are scaling to your best knowledge and to the, let's say, specific physical phenomena you're trying to find a trade-off between. And then one of the key takeaways from our analysis was that the fuel cell dominant variants are always outperforming the battery dominant variants, especially for long range intercity eVTOLs. And for a 3,000 kilogram eVTOL, we found that, about 340 to 380 kilowatt fuel cell system size, 15 to 25 kilowatt hour battery, and a 25 to 35 usable liquid hydrogen storage is where the optimal is. And we'll be working on refining this modeling framework to really find that answer. What are the optimal specs of these different components and the thermal system that would go along with it. So with that, I'd like to conclude, and we'll be happy to answer any questions that you may have.
Thank you so much. Fantastic presentation, both of you. I must say, I'm always happy when I see charts that I've never seen, a couple in particular that were really well done. So we've got a few questions. And by the way, we can stay on a few minutes longer to get to the questions if you all can. First up, we've got Doug. Doug, would you like to come on and ask your question? Say your name, who you're with, and what you guys do, and your question. And please keep it brief so we can get to all of them as much as possible.
Sure. I'm Doug Starfield, Senior Systems Engineer, Energy Systems with Methyl Carbon Ventures, a non-carbon hydrogen fuel. It's still in research and development. And I'm just asking now about the anion membrane solid state fuel cell, if that's been examined in simulation to see if it would be of any use. And also because you wouldn't have to have the platinum, or at least as much platinum in that for the catalyst part.
Sure. All I can say is I am exposed to very tiny bit of work that we're doing in this space. I can follow up with you on that. In my so far experience, we're working on primarily, how adaptation of these automotive fuel cell technology. Some of these advanced topics that are happening, they're more in our headquarters in Aachen from Marius, who's the kind of the person leading out some of these advanced research topics. So I would have to follow up with him to see if we've worked on any anion solid state type approaches for further lightweighting. But I think you or somebody else asked a question about high temp fuel cells, so we are working in that space as well.
Thank you. Thank you very much.
Awesome. Next, Nick, you're up. You had 3 questions. Go ahead and say who you're with, what you do, and your name. And just go ahead and ask all 3 questions. Yeah.
Hi, I'm Nicholas Sangara. You can call me Nick. I'll be quick. I'm with Monroe Defense. Just a couple questions, nerding out with fuel cells. The first question is, did you do any look like the stack you benchmarked? Was that a graphite or steel bipolar plate?
That was stainless steel, but I can check that. Most commonly, so let me see where. Yeah, this one right here. My understanding that this was right here, made from stainless steel.
Okay. Sorry, I missed that in the fine print. My apologies.
No problem. Yeah.
Out of curiosity, what was the voltage of the stack too? Because when you were mentioning like part of the weight out of the fuel cell system, just trying to picture how many cells that they put in there.
Yeah.
For that influencing the weight.
Yeah, I would say it would be 250 to 300 volt system. I would again have to go back and check what was our number, but this is just one of the stacks or one of the fuel cell system that we benchmarked. Just because we decided to take this data because we thought this was the most recent designs and more optimized for and probably the lightest among all the different other systems that we benchmark.
And last question before I turn everything over, out of curiosity, where does the humidifier fall in the in your weight breakdown? And have you done any work like with the humidifier or anything like that for this spec?
My assessment would be that falls in this cathode air system space, but that would be the only one where I can see it falling.
And did you do like any work on the humidifier too as well, or because I know that's very critical for the PEM for its operation.
Yeah, I mean we have done specific humidifier testing, modeling, but we, of course, we don't make any components, so we offer these kind of services to tier ones who are developing these fuel cell systems or OEMs who are trying to understand the systems better. So yeah, I mean we have tested them, we have modeled them, also support tier ones in design of them, but at the moment we haven't really explored into how to adapt some of those for aerospace application.
Thank you.
Great questions. Okay, I just have a couple comments and then one more question. I'm not going to say my questions as questions, but on the plot where you had altitude, I'd be interested to see like up to 60,000 feet on that one. I'd just be curious to see if it kind of continues on that path or does anything different. And then another thing I would like to see is where on the chart before, like a few back, where you had the different pressures for different types of vehicles, I'd be interested to see where like a small fixed wing, if you can go back, I don't know, maybe 3 or 4, it was before this. Okay, this one. I'd be curious to see where fixed wing, I mean, it looks like a VTOL, and maybe it's sort of inclusive with fixed wing. If it isn't, I'd be interested to see where fixed wing would fall, like a small fixed wing 1 to 4 passenger aircraft would fit. Okay, Doug, By the way, great chart. I love this. This is one of my favorite charts. I've never seen this, and I can't see where it came from, but I will when I look at the slides. So I'm definitely going to be using this. Okay, Doug, last questions, and then we'll wrap it up. Or did you already ask them?
I asked about the membrane. I just wanted to make a comment about the graphite plates. It's a no-win. You can't put graphite plates into a fuel cell stack without the problems with the fragility. I worked with company JTech Energy on that, and we finally went to stainless steel plates on the end plates. So I would stay away from graphite altogether.
Yeah. Being added as a compound for getting more durability. That was the only reason that folks were using. It still has the backbone of a kind of metallic plate.
Awesome. Very good.
That's the only comment I had about that, because I had actual lab experience with it, and it was a failure.
Thanks, Doug. Okay, we're going to wrap up. Thank you for staying 5 minutes over. Everybody, please give a humongous virtual round of applause for our fantastic speakers today. And congratulations, Ben, and thank you for suffering through your coughing. I feel so bad, but yeah. Thanks a lot so much. Looking forward to learning more about you all, and really great job. Have a good rest of your week, everybody.
Thank you, Danielle. Thanks, everyone.
Thanks.
Like,